So, folks asked me to give a talk, and those of you who know me, so I'm Rich Maclin. If you haven't had me for a course, I've been with UND since '95, so 23 years now. So my specialty is actually machine learning and artificial intelligence. So those are really my favoriteest sorts of things in computer science. And I like talking about those, but I got thinking about the whole notion of execution, and find one of the things I geek out on is the whole notion of how computer languages actually work, how you actually generate code from those. And one of the things we notice sometimes is that some of our students haven't heard some of the terminology. And I'm teaching a course on compiler design, but it's not a terribly popular course, although we have 21 people for this coming spring, which I think is more than the entire total of everybody who took the 3 previous versions I taught of it were. And those have been taught over the course. I mean, like the last one was 2009, and before that was like 2004. You know, people kept talking me into teaching it, and then nobody ever showed up. But this time people are actually showing up, so I don't know exactly how to take that. But this is sort of the intro to that course, where I'm just going to try to talk to you about how all the different things fit together and try to talk about the different terminology that we use. And if it's review or if it's over your heads, please, you know, let me know to jump past stuff or to, you know, go into more detail. So it's just an overview of some of these ideas with lots of details left out, because I can teach a whole course on this stuff, and I will. And feel free to ask any questions you like. I will try to answer them as best I can. Okay, so seems like a pretty basic notion. What is a program? All computer science people should know that. But it's a good place to start for what we're going to talk about, and how do programs actually happen inside the machine. So how do we get to them, and how do they actually work? So when we say program, people are often referring to suites of programs. So a whole bunch of what we would properly call executables that do different things. So in a database, for example, you may have a daemon process that runs all the time and just sits there and waits for requests to happen. Okay, so that thing is constantly running and just waiting. Okay, almost anything that answers request is something that's going to be sitting there and running on the computer and going, I'm ready, pass me a request, and I'll give you responses back. Now, it generally doesn't do the actual responding. Okay, it's not really efficient to have something that's just sitting there waiting and waiting and waiting actually be doing the responding. So oftentimes the daemon turns around and invokes other things. Okay, so if it's a database, for example, you're going to get queries, and queries need to be optimized before you actually run them. So you'll have a whole query optimization process. Then you'll send that off to an actual execution process, which, if it's a big database like Amazon, you know, you're hitting it up for stuff about different products, it'll look it up in different databases, so it'll actually split the query up. There may be analysis programs in them. Okay, so there's all kinds of things that go with the notion of a program. Okay, so the notion of a program really doesn't mean much to us. We really need to be thinking in terms of executables. Now, what exactly is an executable? Hopefully those of you who've taken 2521 are used to building machine language code through assembly language, so you have some idea of what that is. Okay, and if you haven't, it's just basically lowest possible level code. We can think of something that's actually going to be capable of running on the machine. Okay, so it's generally machine, sometimes intermediate form. So we'll come back to the whole notion that Java introduced the Java intermediate code. But something to be executed by the machine. Okay, so executable is going to include any necessary data. Okay, so it has to have all the data, like if you're going to say something like hello world for your very first program, then somewhere you have to have stored that the string you need is HELLO space WORLD exclamation point. Okay, kind of obvious, but something you need to do. Includes space necessary to run the code, and it's built on the genius of, and admittedly it seems like a very obvious idea, but the original John von Neumann architecture, and that is the notion that the code and the data are all stored in one place. Okay, we have one memory and everything is stored there. Because originally, when they started talking about computers, they imagined a program store and a data store. Okay, and keeping the two separate. And that created all kinds of problems. Okay, so we don't do that anymore. Everything is all in one place. So code, data, we don't distinguish between them. And it makes things a little hairy, but also really makes it possible to make code work. Okay, so in order to start talking about an executable, we need to talk about memory. Okay, so inside your computer, there are a bunch of chips. There are your random access memory. There's also other things. There's your cache. There are registers directly on your CPU. There may in fact be other sources of storage that you have inside the computer, but for our purposes, we can simply visualize memory as a long list of bytes, or sometimes we think in terms of words, so 32 bits together or 64 bits together, but some sequence, each one given an address. Okay, we've got one long street memory, and we refer to individual addresses just by giving each one a number, starting from a low number up to a high number. Okay, so that's our memory. Okay, now again, in practice it's more complex because we not only have memory, we have registers, we have cache. Oftentimes nowadays most processors come with more than one level of cache, so taking advantage of those different levels is key. And basically the idea behind registers and cache is everything costs a certain amount of time to go get when you talk about data. If you have to go out and actually read it from a hard disk, they're really fast nowadays, but it's nevertheless an eon in computer processor terms to get anything from a disk. Okay, so you want to avoid doing that as much as is feasible. Okay, so cache is generally on the chip or right near the CPU chip, so it's much faster because it moves at the speed of the electronic circuit. And registers are built into the CPU, so they're really close. Problem is you have a limited number of the things that are much faster. Okay, so this is where you trade things off. And virtual memory is the idea that in the worst case, if we actually fill up all of our actual memory, we can have the disk pretend to be extra memory, which just gets ugly because bringing stuff off of disk is very, very slow, so your computer slows down horribly and you decide you need more RAM in your computer, or you need to kill some programs off, or whatever. Okay, but that's the problem you're running into. Every time you start using virtual memory, you're likely to see slowdown problems. Okay, so what does it mean to run an executable? Okay, so an executable is a sequence of code and data, and I'll show you what I mean by the sequence, and there's some extra pieces that are going to actually be added, but it's asking the OS to load an executable from a location, so find it out on a disk or possibly on a USB drive, somewhere else in memory if possible. Store the beginning address of the code. Okay, so we store that in a register, and that's actually going to be one of the key things that's going to make it possible for this to work. And then we're going to set the program counter for the start of the actual instructions, and please ask the PC to start there and start executing. Okay, and that's basically the notion of how one of these things actually happens. So how do you make one? Okay, so this is where we start getting into the language of how do you go from a high-level piece of code to something that actually can execute on a machine. Okay, so what does an executable really look like? Well, the yellow and the blue part are the things that are the actual executable stored out on the disk. Okay, so the yellow part is some sequence of machine instructions. Now that may be not just one function, it may be several functions. Okay, all of the different functions that are important to your particular piece of code will be stored in there and in whatever particular order. Okay, they're simply referenced as these different functions. In addition, you'll have global data and constants. Anything that you say is something that is outside of any structure is global. Now that includes references to all the functions. Okay, so that's what's actually stored on the file. Okay, now you've all seen high-level languages. They all have some things in them that actually make it tricky to run them simply in this form. If you just had the yellow and the blue part, you have all kinds of problems. Okay, how do I deal with function calls? Okay, how do I deal with allocating new data? Okay, and this is where the operating system provides you a little help. The operating system will ask you to, it's basically when you're saying, I want to run this, you say, okay, here's where the executable is, and I'm going to need some extra space. Okay, and the operating system will very nicely say, okay, you can have this much to start. Okay, now, that extra space is great. That makes it possible for us to run functions. It makes it possible for us to declare new variables that we create out of the blue using things like dynamically allocated variables, so things like the new function. Okay, so I'm creating new, and I'm going to tell the computer when I'm done with it. Okay, that's actually the key difference between those notions. So there's things that appear on what is called the stack. These are things associated with function calls. So the idea behind that is when you call a function, it has a certain amount of memory you're going to have to put aside to make that function run, and it stays around until the function comes to an end. Okay, but that's very predictable from within the code. When the function comes to an end, you can make all of the memory that you put aside for that function go away. So we build it as a stack, literally, although it's a stack that grows downwards, just tradition. The stack always comes right below the global data, and the heap seems to always come at the bottom. So it's the heap. The heap is the dynamically allocated stuff. And this is stuff where you say, I want to create a new variable of this type, or a new array of this type. And I set aside data for that. Okay? Now the thing is, that may go away quickly. You may use it for one instruction and never use it again, and you don't need it again. So it should go away. On the other hand, you may hang on to it for the entire length of the code, even through many, many functions, so it might stay around for a long time. Okay, so that doesn't go away in sort of an easy, straightforward way. So we put it in a different portion of the code. Now, some things to note about this. The brilliance of this approach is, well, okay, the heap can be a problem if some gets allocated and deallocated and you have little holes in it that are too small to use for anything. So this is one of the things that often leads to what's called memory leaks. People allocate things, deallocate things, they're not making very good use of their heap, and the heap keeps growing bigger and bigger because the computer keeps having to ask for more space. But it's that asking for more space that's kind of brilliant. So if I'm running a particular piece of code and it gets to the point where the stack and the heap get really close to each other, all the operating system does is say, okay, I'll give you a bigger section of code. Okay, so it says, copy, if I can't extend the bottom of your section of code, I'll move you to some other location. Okay, and all we'll do is pull these things apart. So move the heap down to the bottom of that location, leave the stack where it is, and now you have more space in between. Okay, now how can this possibly work? Okay, I mean, you're moving it around in memory. The address has just changed. Okay, and this is the other key thing in the whole von Neumann approach. As long as we're treating the memory as this logical sort of thing, we make sure that we don't put any actual memory addresses into the actual code. Okay, you notice I said we store the top of the code. So the system keeps track of everything where the machine code is by remembering what's this first address. And it stores that in a register. So when you say I need to go to this location, logically it's simply an offset from the top. Okay, so you don't have to know a particular location, you simply have to go look up where's the top, and I want to jump to some location from there, some offset. Okay, same thing with the stack. As long as you know where the top of the stack is, you can refer to any part of it as an offset from where the stack is. And the heap is a negative offset. But everything's offsets. Okay, so it doesn't matter where in memory the code is. Okay, the only places you need to change are the places where you store those key values. Where's the top of the actual code? Where's the top of the stack? Where's the bottom of the heap? Yes?
When you do that involves copying that whole thing, the stack, the heap, the memory.
If you don't, you're hoping that there's space in memory directly below the current heap. But that doesn't often happen. So you often end up moving the entire thing. And it's a costly operation, but it's memory to memory, which is normally pretty fast.
Even if there's space below the heap, you still have to copy the entire heap down.
You have to move the heap down. Yep. And, well, I need more space. I'm getting to the point where two things are coming together. If they come together, I'm not going to be able to call another function or allocate anything else on the heap, and the code will simply die. And some code does that. And you can be smart about it. Most times when you run code, you can actually tell the system, I want a segment that's this big. I know that looks really gigantic compared to the size of my code, but I'm going to allocate a lot. Okay, so Java especially does a lot of stuff where it allows you to say, how big a segment do you want? Okay, so, trying to remember, did I have any? This is most of the basic notions. Oh, and I tried to give you a little bit of an example of a very simple piece of code. So, the code has a global variable z, which is a string holding the string value hello. I have g, f, main functions. I have local variables within f and b. I have a y, which is going to be where I'm going to store a thing allocated on the heap, and x, where I'm going to store something allocated on the heap. So how does this end up getting laid out? Okay, well, the system goes through and compiles this into executable code for main, for g, and for f. Okay, so somewhere in the executable file, you'll have a sequence of instructions that corresponds to how to make main work, sequence of instructions that corresponds to how to make g work, and a sequence of instructions for how to make f work. The global variable gets stored here. You'd probably actually in most systems store the locations of g, f, and main there, because that'll make it what offsets they would be at within here, but there's a couple different ways that people do that. So it's not guaranteed that it would be done that way. Now I'm imagining that the execution is at this point. So main called f, which called g, which has now reached this particular point. Okay, in terms of what it looks like in the computer at that point, there's what's called an activation record for main, an activation record for g, and an activation record for f, and they're a stack but built downwards. Okay, so main was called first, then g, then f. Okay, I'll talk a little bit more about the notion of an activation record. And since I've already allocated x and y, the space for those big arrays is sitting somewhere in the heap. Okay, and if I've stored things to them or changed values there, they're in that location within memory. Okay, so does all this make sense so far? Okay, so let's talk about some details. So again, in terms of machine code, generally we're talking about the notion of the machine this is to be run on. There are such notions as cross-compilers, so programs that are actually able to generate an executable for a different machine, okay, which is a lovely, useful thing. Again, machine code relies on the offsets. Okay, we don't try to figure out where you're going to be in memory, because who the heck knows? The operating system is going to put us wherever. So what we're going to do is we're going to track those key places. Okay, where's the bottom of the heap? Where's the top of the stack? Where's the start of my segment? If I know those three things, I'm pretty good, because I can calculate everything else with offsets with respect to those basic things. So it's actually really easy to move my code. So we often say at the start of the executable, the current activation record, the current top of the stack, open areas of the heap, so there may be other things as well. And to give code more space, you simply move the heap. Okay, so let's see. I think I did activation records at the very end, so we'll come back to those in a bit. So, how are executables actually made? And I should say, the notion of an executable is often something, especially if you're using Java, there isn't a corresponding executable. Okay, so Java doesn't produce executables, it produces intermediate files. So let me talk about all the different terms I'm throwing around there. Okay, so in general, executables are built in assembly or machine language, and the assembly tends to deal with names for locations, so that's the major difference between assembly and machine language. If you're building in a high-level language, there's various things you might do. So you might compile all the way to an executable. Okay, so that's all the steps from a high-level language all the way down to something machine code that looks like one of those executables that I talked about, the yellow and the blue parts. Okay, so that's one possibility. There's often compiling to intermediate forms. We still use the word compile, although arguably you're not going all the way to executable, so is it really a compiler? You'll get people arguing about that. So compile is generally a term we use to say we're taking it from a higher level to a lower level. That lower level doesn't have to be all the way to machine code. So, for example, you may have noticed when you're doing C++ that your system has a lot of files when you compile things in individual files, each of them ending in .o, right? Okay, well the .o's are intermediate forms. They're actually what's called relocatable code. Okay, so they're a little bit like assembly code, but where you don't resolve any of the things that are non-local. So if you have a reference to a library that's in someplace else, that library is not actually in that code. So you're only compiling up the little bit of code that was in that file. Okay, so that's an intermediate form. Java has something called bytecode, which you've seen .class files for, right? Everybody seen that notion? So Java came up with it seemed a little odd at the time, but it turns out to be a brilliant idea of making your code go in 2 steps. So your Java code gets turned into an intermediate form called bytecode. Bytecode is stored in classes. Okay, now when you actually want to run it, you invoke the Java interpreter, which interprets your bytecode. Okay, and what it does is it reaches out for all the other things it needs based on how you've built your structure. So I'll talk about that more in a bit. Okay, so all of those things are often referred to as compiling. Now, when you take things like those .o files and libraries and pull them all together and make an executable out of it, we call that linking. Okay, this is generally because there isn't much high-level language stuff left. All you're doing is linking the things together. So I have a reference to something out of the standard I/O library for C++. I'm going to go grab that code and say, okay, stick it in here. I'm going to need that. I have a reference to, what was my favorite? The curses. It's one of my favorites. I need a function from there. I'm going to go grab that and stick it in here. So you compile things together. It's called linking in that case. Okay, you're pulling all the things together and making sure everything lines up. And the interesting, weird thing about linking is that most linking systems will actually let you have more than one version of things sitting around. So the order that you list the .o files and the libraries in actually matters. Because whenever it's trying to find something that it needs to refer to, it'll look through all of your .o files and things and pick the first one. Okay, so if you've ever run into problems where it's, why is it not using my version? There may be a version in a different file that it's finding first during the linking process. Just one of the weird effects of using linkers. So now how do we go straight to executables? Most compilers actually hide the fact that what they do, if you're going straight from your code and the code has all you need in one thing, it compiles and then it passes that off to the linker without telling you, oh, by the way, I'm invoking the linker for you. Okay, so oftentimes the compilers only ever go to an intermediate form and it's the linker that produces the actual executable. Is all this making sense? Is this stuff you care about?
Yes.
Okay.
Yes.
So, interpreters. What exactly is an interpreter? Well, unfortunately, there's lots of possible interpreters. Like your average operating system shell is an interpreter for that shell language. So when you type commands to it, you're typing commands in a language, and it's a online interpreter in that it's responding to your commands one command at a time. Okay, not all interpreters work that way. Python is an interpreted language. Okay, now it literally goes through and reads all of your code and builds all of the code into a tree that it's going to execute, but it goes through and looks through it all before it actually tries to execute. Okay, not all interpreters do that. Some interpreters look at this command, then this command, then this command, and they'll execute them, and then they'll run into the error command and go, oh, well, this one has errors in it. I stopped here because that one works and this one doesn't. So you get different responses from different types of interpreters. Okay, but most of the time the idea behind an interpreter is you're working on the code directly. Okay, so I don't know if I should have bothered putting this in. So I just wanted to talk about the notion of different levels of languages is one we talk about. You know, the whole idea behind high-level languages was to get at some of the notions of it'd be nice if our language was closer to English. And there are folks who actually continue to do research in something called automatic programming, which is the old Star Trek thing. Computer, please tell me how many beings there are, how many humans there are, or humanoids there are on the planet. Okay, well, it'd be lovely if you could program like that, but of course this brings up questions like, okay, what do you mean by the planet? How am I supposed to figure that out? What do you mean by humanoids? Okay, what qualifies? Okay, so it's not an easy sort of thing to answer, but it's a very interesting question. And this is, computer programmers actually seem to be trying to push closer and closer to the boundary of being able to let people program for themselves through natural language, but we still seem far away. So I wouldn't expect it anytime soon. Machine language is obviously where we started. People literally did program in machine language. Assembly language came in basically as a, I keep having to come up with numbers for these things when I should just use names and let the system figure out numbers for me. So that's mostly what assembly language did. And then along came high-level languages. Actually, most of the high-level languages started out, including Fortran, was probably the first really big one. And Fortran was an IBM person who didn't like sitting there and writing the same stupid assembly language code again and again and again. I want to print out a string. Okay, I got to write a loop that goes through the string, one character at a time, and provide each of them to the screen, and that gets really boring and really old. Couldn't I just have a formula that says, I have a string, please write the string one character at a time to the screen? So he came up with this thing that he wrote a program to translate formulas that he put into a language into the corresponding assembly language, and he called that his formula translator, or Fortran for short. And it's why it's the only language that kind of doesn't live by any of the rules of how computer languages tend to be built now, because he built it without knowing anything about language. But weirdly enough, it's also probably the only language that easily automatically parallelizes, and there's some specific reasons for that. So this is sort of the two groupings of high-level languages. I picked out just the ones that are considered the most popular based on what computer programmers report they're working in. So Java, C, C++, Visual Basic, C#, Go, and then the interpreted sort of ones, special ones, Python, JavaScript, PHP, and SQL. And yes, there's a good chance you may work in JavaScript or PHP, and I'm sorry. Just the way it is. Okay, so, and I should also point out that we also talk sometimes about different programming paradigms. So you're mostly going to be used to the notion of imperative languages, ones where you have computation as a series of actions. So they are often the easiest to translate into machine language because every action in a high-level language corresponds to some sequence, generally, of actions in a low-level language. There's object programming, the whole notion of organizing computation around objects and functions that can be applied to objects, which C++ and Java aren't really object-oriented languages. They have object-oriented aspects to them. But you want to look, there are actual direct object-oriented languages like Smalltalk, which is just pure objects. The only thing you've got are objects and messages between them. And it's actually very interesting to write code under that paradigm. There's functional programming, so Lisp is probably the most classic example for those of you who've done Scheme. Pure functional languages where often the syntax is very simple, but you can do very complex things with it. And even logic programming, which Prolog is probably the most famous version of. And that's literally where you define a program in terms of, this is what the problem I would like you to solve. I'm going to phrase that as a logical problem. Now please solve it for me. And code follows from that, which is it's a weird thing, but kind of fun to play around with. Okay, so this kind of takes me to the second part of how much time do I have? Where are we?
20 minutes or something.
As much as you want.
I don't think everybody would agree with that. I hope there's still enough pizza for people. Okay, so how does a compiler actually do these things? So this is a rough description of a compiler. I kind of wanted to go through this just to mention some of the steps that you may not realize are in there. Okay, so some compilers may use some or all of these steps. Some do optimization more than once. Linkers don't do the optimizer, I should have said not the optimizer in the code gen in general, or I'm sorry, linkers do the optimizer in code gen, and interpreters tend to skip the code generation parts. Okay, but there's no guarantee. So the basic idea behind a compiler is you take your source code and you want to eventually get out some sort of focus of object code. So executable, possibly an intermediate code, and you go through a series of steps to understand it. So we have the notion of a parser and a scanner. So the scanner is something a parser uses. So a scanner is something that turns the sequence of letters that you type into your code into meaningful tokens. Okay, because it doesn't really care about things like spaces. Okay, you throw in lots of spaces, it doesn't care. You throw in comments. I don't care about those. Those are not for me. Those are for the humans reading the code. Okay, you can space things differently. You can do all kinds of interesting and weird things, and the computer does not care. So scanners simply go out and get the next token, and I'll show you an example of that. Now, parsers have a description of what are legal sentences in the language that you're working in. So the idea behind a parser is you go through and you map the tokens that you're given onto what legal sentence could they have been making. So the idea is you want a language that doesn't have the possibility of people making weird sentences. It's one of the reasons English doesn't work, because you can do, Mark Twain kind of famously skipped in and out of grammar. It doesn't matter. It's brilliant writing, but it's brilliant writing in part because it is sometimes ambiguous. Okay, you can't have that in a computer program. We don't want a language where you can be ambiguous. Once I've gotten through understanding it in terms of sentences, I do something called semantic analysis, and that generally involves, okay, I've sort of at a gross level identified that these things are sentences. Do these sentences use things in ways that are allowed? Okay, so I'll try to give you some examples of that. Now, once I get to that point, I start thinking about actually generating code. Okay, so oftentimes what I'll do is I'll generate some intermediate code, often something like an assembly or a virtual version of assembly. And then I'm going to do something called optimization. Now, why do we do optimization? Because this process of automatically generating code often includes code that goes through, so it'll say, jump to this location. And this location will say, don't do anything because this was an if that didn't have an else. And then that will say, jump to this location, which in fact is also nothing. So I could have gone back and found the location this one's going to end up and said, jump right over that stuff and get to here. Optimizers look for that sort of stuff. Okay, they try to go through your code and strip out stuff that you would look at and go, why would you do it in that dumb way? Why don't you take out some of these intermediate steps? Now, optimizers can do really magical things, but they also can be a little scary. You notice, by the way, when you use like GCC, you're using the optimizer at level 2. Okay, you can actually go in and request that it use the optimizer at level 3 or even level 4. The thing is, level 4 is not safe. Some of the optimizations will actually change how the code works, which sounds like it shouldn't be called an optimization, but for many things, the code is correct. You simply have to worry about some of the edge cases. Okay, so that's the optimizer step, and then finally you actually go through and generate the actual machine code. Okay, so I want to just give you a brief taste of each of those things. Yes?
The parser to match to sentences, does that use regular expressions, or
No.
could it?
I can't use regular expression. So a regular expression cannot match up parentheses. If you've been through the course,
yeah.
and I want a left curly brace to be matched by a right curly brace. So we have to use something more. Now, scanners almost always use regular expressions. So we use some form of grammar and then various grammar parsing mechanisms, and I didn't want to go too much into those here because, again, that's getting into real deep details that you don't necessarily need to know for this class. Now, for this purpose, for my class, you're going to have to learn all of that stuff in gory detail. So, I'm giving you fair warning, anybody who's already signed up for my class. So, what's a scanner do? A scanner simply goes through your code, looks at it, and turns it into meaningful tokens. So tokens in English are things like a word, a capitalized word, a period. Okay? And some of these things you can actually hear in spoken, although it's harder to determine whether or not something is certainly capitalized in spoken, but sometimes you can get that out of it. Periods and commas and things aren't always obvious, but written, certainly you can see that. So dogs like chocolate. So this would correspond to a sequence of 4 tokens, a capitalized word dogs, a word like, a word chocolate, and a period. And that makes a legal English sentence as far as I can go. Okay, and so the scanner's job is to turn things into tokens. It's the parser's job to decide if that's a legal sentence. Okay, now scanners notice things like illegal characters, something you put in that doesn't belong there. Okay, and generally they're done, as you asked, with regular expressions. I think I just gave a piece of code here with all the tokens you might get out of this. So here's a piece of code. I think I did it from C++. So a reserve word int, an identifier main, a left paren, right paren, a left curly brace, left paren, right paren, left curly brace, reserve word int. Yeah, I missed the A. So there should be an identifier A. I missed that. So identifier A, the equals, the 0, semicolon, identifier C out, double left angle bracket, the A. So we come up with something that says here are all the logical expressions, generally using something like regular expressions to say here are all the legal things that you can say as tokens in this language. And oftentimes they're simple. Some of them are complex, like if you want to define what is a legal double. Okay, well think about all the things you got in there. You have a possible leading plus or minus, so you have a plus or minus sign possibility. You can have digits before the period. You can have digits after the period. You don't have to have a period. Okay, you can have an E, either lowercase or uppercase, after the whole thing to indicate an exponent. You can then have a plus or a minus optional after that. And if you're going to have an E, you need numbers after that. And somewhere along the way, you have to guarantee that there's at least one digit. Okay, some languages say you have to, if you're going to have a period, you have to have a digit on both sides. Most of the time, C will let you get away with, C++ will let you get away with having only a digit on one side, but you have to have at least one digit. You can't just say plus point E06, and that doesn't make any sense, even though it's pretty close. Okay? So that's the basic idea behind a scanner. Now, a parser has generally a set of rules, so it's literally defined as a language using parse rules the way that we define regular human languages, where it says, okay, this is a legal sentence. So I might have a legal sentence that says, okay, you can have an identifier followed by an operator followed by an expression. Okay, well, identifier, operator, and this thing's an expression. And an expression is a recursive thing that says, okay, expressions may take the form of left value and right value with an operator in the middle, where the left value and right value can themselves be further defined. Okay, so we get this very complex grammar that says you can end, which is why the language can get arbitrarily deep. Okay, now what we generally do with a parser is we're taking what they wrote and turning it into what we call an abstract syntax tree. This is basically a representation of the code, but where a lot of the ambiguity's gotten out. Like, we use parentheses in code to indicate that these two things go together and need to happen before this operation happens. Okay, in an abstract syntax tree, you never need parentheses. Okay, the parentheses are irrelevant. So we toss out anything that's actually just sugarcoating. Okay, there for syntactical purposes. Okay, so we're trying to turn out something that's an abstract syntax tree. Now, the sorts of errors you get here, and a lot of the errors you get in code come from parser, are, this doesn't make sense to me as a sentence. Okay, so I do A equals A times 5, and it's not Python. I leave off the semicolon, and the next thing is on the next line. It says B equals, and the computer gets to the B and goes, hey, this token doesn't make any sense. You have A equals A times 5 followed by a B. Did you mean 5 times the B, or I don't know, you gotta tell me, this is stupid. So you get an error that says at this location, basically starting right after the 5, I was expecting, and oftentimes the system can say, here's the list of things that I might have seen. Could have been a semicolon, it'll give you a list of all the things that could have been reasonable ways for you to continue. You could have added another operator. You could have put a semicolon, so there's things you could do. Okay? What you did was one of them that you can't do. So this is an error. Now, parsers are very good for that sort of stuff. The only problem you run into is oftentimes when we're writing parsers, we want to give all of the errors in the code instead of finding the first one and stopping. Okay? Now that's actually a tricky problem, because if I left off the semicolon here, okay, I drop that. Okay, I run into, this is an error. Now what do I do to go on and look for further errors? What do I do with the a equals a times 5? Do I discard it? Do I try to figure out what they meant to say? What if what they meant to say was to declare a local variable that's actually important in the next statement? Okay, if I don't keep it and try to figure out what they were trying to do, I may get an error in the next statement that says they didn't declare this variable. So it can get ugly quickly, especially if you leave off right curly braces. Okay, because you're not telling the code where things are actually supposed to end, and that's a real problem for it. Okay, so one of the things you'll notice in a parser, once you see one error, you may get lots more errors after that. Oftentimes that's because it tried to make a decision about what you were trying to do, and it made a poor one. Okay, so sometimes you fix the one error and suddenly all the other errors go away. This is because it's trying to do an alignment. It's trying to guess. Where did you go wrong? What did you mean to leave out? And there's no way to know. Okay? It can't really figure out what you were thinking in your head. You might have simply just left off typing. So, this is the types of errors you get from parsers. Okay, so I gave you an example here, a equals times 5. Well, okay, a equals, but then times, that doesn't make any sense. So now it's got to figure out what to do from there. Okay, now we have the semantic analyzer. So this is the thing that checks, do all of these things make sense? Okay, so it may notice type errors. It may notice that you're referencing something that doesn't seem to exist in a particular class. Okay, and there's a whole structure for how to do that, something involving something called symbol tables. That's really a deep detail, and that's definitely something I'm not going to try to cover today. Okay, so, but there's some simple things it'll do to try to help you out. So it might look at this and say a equals 3.0 times 5. And the thing is, in most languages, in the machine language, you have to perform arithmetic operations on the same type of thing. Okay, so it sees 3.0, which it assumes is a float or a double, and it sees a 5, which looks like an integer. Float times double doesn't sound right, or float times integer doesn't sound right. So oftentimes a smart compiler will throw in a thing that says, okay, they must have meant convert this 5 up to a double, and now that'll work, and then it'll check that type against the A type and say, okay, the thing we're storing into is a double, so we're good. Now this is another potential source of problem for you, because there's a lot of things that a compiler will do that are helpful, that may not always be helpful. One of the things is it may look at something and say, you use something of this type, and I can convert that type to a higher level type automatically for you to make the fact that you're setting this equal to this, okay, because this type is type A and this one's a subtype of A, so I convert this to an A and that's good, except you didn't mean that and that's going to cause you all kinds of problems. Okay, so that's one of the things, and so oftentimes it will complain that there's a mismatch between the types. Okay, so this is the type of thing that's caught in the semantic analyzer, and this is something that goes through the abstract syntax tree and basically asks, do all of these sentences now make sense given all the types and all the classes and the dereferencing that you do from those classes? Make sense so far? Okay. So, then we get into intermediate code generation. And oftentimes that's done in the form of some code that makes sense to a actual code generator. And we often use code generators repeatedly, and we generate intermediate code from different languages in a form that a particular code generator can actually use. So a famous one, for example, is 3 address code. So limiting instructions to anything that involves at most 3 addresses. Okay, so if I wanted to do initial plus rate times 60, okay, well then I might set up a local to be that number 60, take that local and multiply it by the rate, add initial to that local, and then store that result in variable A. Okay, and the temps become stand-ins for, okay, I'm going to need extra space to do some of this calculation. Okay, so that puts it much closer to machine language. Now, I mentioned at the beginning I was going to talk about Java. I keep having people walk out. Is this getting really boring or just mildly boring? Is that what, anyway.
It's super interesting.
So Java code is set up to be something like 3 address code. So the stuff in your class file is written in a language that's universal. It's bytecode. Bytecode has a very specific machine format that isn't really machine code. It's something much closer to this. It's very much like 3 address code. And the basic idea is your Java interpreter knows how to interpret 3 address code, the Java version of it, the bytecode, on that particular machine that you're running on. Okay, so it simply reads that in and executes it, but it has to interpret it because it's not really in machine code, it's at a higher level. Now, when Java first came out, that was Java's big drawback, was it was much slower because you didn't do all the optimization. Okay, now the Java people have gotten very smart. Okay, they've done a lot of on-the-fly optimization of the code. Okay, so Java is often almost as fast as code generated with other languages nowadays. So that's one of the areas that people are doing further research in compilers in. So it's not kind of directly in languages, it's more in how to effectively use the languages. And another big one that's very popular now is also kind of related to this notion. That is that one of the things we are very interested in working with modern CPUs is dealing with pipeline. That you're often trying to execute, 100 instructions ahead. Well, that means you need to be looking at the code and figuring out where are key places where you're going to branch and try to guess which branch you're going to go down, which you can imagine is an ugly, ugly thing to do. But if you do it effectively, you make your code go fast. Okay, so there's a lot of people who look at that sort of stuff. Because if you start executing something and you find out you're not going down that branch, you just wasted all that calculation. Okay, so past intermediate code generation, we have optimizations. Okay, and optimizations may look at the code and say, well, that was kind of dumb, the direct translation you did. Why don't I just stick in a 60.0 here, so break this down to this, and then I can just say, since it's still 3 address, a equals initial plus temp2, I only need 1 local variable, and I'm down to just 2 instructions. Okay, so again, the automatic generation tends to be very safe. The code always works, okay, but it uses a lot more instructions than it needs to. So we use the various optimizers to compress that down into a smaller number of instructions, which goes faster. And like I said, there's actually levels of optimization, and most systems, like the GNU compilers, include 04, which I've never seen anybody actually really use in production code because it's not safe, and it's literally documented in the man files for it as not safe. Okay, so that's the optimization process, and then our last process is to turn that intermediate code into whatever machine code we're talking about. So as you can imagine, cross-compile is simply replacing that last step with something that says, here's the machine code for, you're on a Windows machine, but you're generating Mac code, okay. Here's the sequence of instructions you would need to translate these things into code for a Mac. Okay, so, oh, and I did include a thing on activation record. So one of the things people always ask me about, what is an activation record? How does a computer keep track of it? An activation record is not something that the computer actually knows anything about. It's a logical notion that we use. Okay, so what's the basic idea behind an activation record? So an activation record says, I'm about to invoke generally a function. Okay, some sort of method that's attached to something, and I want to call it. And it's going to run for a while, and eventually it's going to calculate a return value or values and then send them back to me. So how do I make that happen? Well, it's tricky because the execution now has to pick up with an entirely new portion of the code. So what do? Well, we're going to set aside space, and we do it on the stack. We say, okay, the function has these 3 parameters, so I'm going to set aside enough space for each of those 3 parameters. And that's going to be where they're located. So inside the code that's actually running on that function, they will know to look at the stack pointer, and at that offset is where the first parameter is located. And the stack pointer plus that offset is where the second one is located. The stack pointer plus the third offset is where the third one is located. So that becomes where the variables are. Okay. Now, if you have any local variables beyond parameters, you would also store them there. Okay. You store the location where you were called from. Okay. This is going to be the last. This is going to be the place you're going to go back to when the function ends. Okay. Now, note, I say it's going to store this. I'm making it sound like somebody else does that. No, when you call the function, you have to set up all these pieces. So one of the things you throw into the activation record that you're building so you can switch control to that function is, where should you come back to when you're done? Now the cool thing is I know because I'm writing the code that's setting up the activation record, so I can say at whatever instruction I'm at plus this number is where you come back to. Okay? We often store the values of registers. So registers are used to calculate temporary things. So oftentimes a function will be in the middle of calculating something. You don't want to throw off all of its temporary things, so you actually grab all of the register values, you store them on the stack. It's safe. And then you have pointers to allow access to non-local variables. So literally the calling function sets up the activation record. Okay, so the local variables exist in the stack. Dynamic allocated variables exist in the heap. So the calling location builds the activation records, switches the code location to the called function. The called function executes, keeps going through, accesses the stack, heap, and globals through the various things. And at function end, okay, if you have return values, you copy them to the activation record right at the top. Okay, because the function that called knows you calculated a value, so you're going to leave the value you calculated at the top of the stack so it can grab it as soon as it gets into control again, and then you undo everything else. So you say, I no longer need this activation record, move the register values back into their registers, restore their control back to the location that I have written in my activation record where I should go back to, and that that location knows, okay, on top of the stack, past the current activation record, should be the return value they got me. Grab that return value and start working with it. So it's a logical concept, but it's one that makes so much of what we do possible. Okay, so it's a key part of the whole execution process. So that was basically, that's sort of an overview of the whole compiler process, but what I wanted to sort of talk about were those things like what is a compiler, what is a linker, why do we have object files, how does Java's process actually work. So I hope that's a little more clear. So, any questions? Yes?
So like the intermediate, like for example, the .o files that you get out of a C compiler, could you then, if you wanted to, could you take those to like a machine on another architecture and then kind of run specifically the last step?
Generally the .o files are so they're intermediate code, but they're in intermediate code that tends to be specific or close to that computers. Not all. The GNU stuff actually has some cross capabilities, so that can actually be translated by other linkers.
Okay.
So it depends on the compiler.
So that thing you mentioned about I forget what it's called, but like the level 4, like the optimization thing.
Yes.
What about
minus capital O4 when you're using G++ or GCC.
All right. What about that is so dangerous that the person who made it is just don't even use it.
You can do a lookup on that on Google. There's some cases where simply jumping past things often misses changes to things. So it can be very tricky to. But I can't give you a.
It is not going to follow the C standards.
Oh, so it's just
Something bad could happen, but it might not.
It might not. It's just trying to get rid of as many steps as it thinks it can, and it's guessing.
Okay.
And it would be better if you could prove it, but it's guessing.
Okay.
One other thing I wanted to mention. By the way, so one of the things you may notice, code sometimes does different things on different machines. You compile it different places, and it runs differently. So one of the things that compilers have big differences on is setting up the initial values of things. Okay? When I allocate things on the stack, I might very nicely go through and reset all the variables to a reasonable value to start with so that they're all 0 or null or whatever. But I don't have to. Most of the standards do not require the compiler to actually do that, so some don't. And that means that the initial value of something could be 0 if you're running into a nice compiler, or could be something entirely arbitrary, based on it's using up some bits that were representing something else just a minute ago. So you never know. So that's one of the things you have to be very careful about, is it's always good to do initialization, to know that the system has set this up so that I don't get any weird results. But that's often when you get weird results of I compiled it this time and I ran it and then I compiled it again and it did something different. There's a chance that's the reason. Anyway, sorry. Other questions?
So how does the linker process differ between, let's say, linking together a bunch of .o files and let's say looking together a bunch of DLL files on this window?
Well, the DLL files are library files, so it's very similar. Okay, those are simply, so the dynamically loaded aspect of that, so the DL part is, it's only trying to load the things you're actually going to need.
Okay.
Okay, and so some version of Windows will allow you to get away with executables that simply have a reference to something that it assumes will exist in all version of Windows, which doesn't always hold true.
Yeah.
But that's so. There's a whole thing to library. So you notice, by the way, when Java, you set up Java, you give it a package has a path, and you notice, like, if I often use paths that say, you know, like edu.umn.d.cs4531. Whatever. Okay, and you notice you end up with a file structure that's edu.umn.d. You know, where's that coming from? Well, that's literally the process Java's using. It knows a few locations where you tell it ahead of time that it may find packages that contain code that actually matter to it, so class files. Okay, so what it's going to do is it's going to look through all of the possible paths that have edu, umn.d.cs4531. Whatever to see if that thing that it needs is located there. Okay, so that's why your path files matter. And the same thing happens with dynamically loaded libraries. And dynamically loaded libraries are basically a group of .o files where you don't have to use them all. You can just use some. And you can actually ask, for example, to generate an executable that includes all of the dynamically loaded things so that the executable will not have to go out and use any external code. But that's, you can get very big executables in that way. So there's good and bad to those sorts of things. Other questions? Okay.
What's your opinion on pineapple pizza?
I think it's meme worthy.
Hey!